Hey, what's up, everybody? Just here, we're doing like a little live screen chat thing, discussion on analog modeling. And I'm here with William. I'm not going to try to pronounce your last name. Fehlberger? Fehlberger? Is that right? No. See, it's terrible. Terrible. How do you pronounce it? So,
Fehlhaber.
Fehlhaber.
Fehlhaber,
Okay. William F. I'll just call you William F. And Jasper Kirton, who's a classmate of mine at Goldsmiths. He's done a little bit of analog modeling as well. And so we're just having this conversation, and I'm just going to go to full screen here. And so we were talking about it. We were talking about it. Funny enough, this is actually our second recording because we were talking about it before, and it just got so deep and so complicated that I felt like maybe I would, lose some of our listeners because, it is a very deep and it's a very tough conversation to really take and break down in a simple way. And so what we're going to try to do is we're just going to try to have a little bit of a conversation about this, about the first steps to analog modeling, what it actually is, and then just some different approaches, and really try to keep this as simple as possible for people that don't have any sort of maybe programming experience or analog modeling experience. Just people that may be curious about what it is, and we'll give an overview, and then maybe later on we'll get into the weeds and we'll start doing transfer equations and transfer functions and Z plane and S plane, and so so let's just start. Maybe I'll start with a kind of introduction to analog modeling, and you guys can tell me if I'm going off path or not entirely accurate. But so let's say that I have a physical piece of hardware like a Moog filter or a compressor or a synthesizer, and I want to take this physical piece of hardware that's working through electrical circuits. It's all electrical impulses, and now we want to take this and we want to try to actually convert it into a software version that behaves in the most accurate way possible in comparison to the hardware version. And then we run into problems with this, with these conversions, because one, we're talking about a piece of hardware gear that's working off of electrical circuits, and electrical circuits can function differently, especially older ones, depending on the weather that you turn it on in. So it may function differently depending on when and how and what environment you turn it on. So, how can we take this and imitate this behavior or make a faithful kind of rendition of it in software? And Williams done this before. So uh, we were talking last week, and you said that uh, you did a Moog filter. Is that right? Uh, so you took a Moog filter and you did a software emulation of a Moog filter. So can you just kind of tell us a little bit about how that how that thought process, how, like, just when you first came up with the idea of, I want to take a Moog filter and I want to do a software version of it. What was your first kind of approach?
Well, there's a couple prerequisites when
Okay.
you get down into it. I'll give an overview. But
Yeah.
some of the prerequisites in the first place are understanding some DSP mathematics. So that's basically all linear algebra.
Mm-hmm.
And then you should terminology associated with DSP.
Mm-hmm.
But then there's also, you have to know some analog electronics to be able to evaluate the circuit.
Yeah.
So just giving a brief, broad overview. First thing you have to do is analyze the necessary parts of the circuit.
Okay.
Not all of it matters.
Okay.
And then you have to create what is known as a transfer function to express that.
And a transfer function is, just to interrupt for people that may not know, a transfer function is a mathematical equation, correct?
And it's just saying output over input. It's a ratio.
Okay.
That's it.
Okay.
Then you have to discretize that. So you have to take that from being in the analog domain, in the digital domain. I use something called a bilinear transform to do that. Mm-hmm. There's a couple of ways of doing it, mm-hmm. but that allows you to set the response, the frequency response or the amplitude response, the behavior of the circuit mm-hmm. at the fixed intervals that you have in the digital domain. Mm-hmm.
And, okay. And just to kind of interject really quickly, when you talk about discretizing something, my impression of what that means for people that may not know is, okay, so let's say that we have my voice and I'm recording it into a microphone. So my voice just out here in analog space, what have you, basically it has kind of an infinite amount of samples. And when we're taking it and we're discretizing it or putting it into discrete time, basically what we're doing is we're sampling it at various points in time really quick, so quick that the human ear can't register it. And that's what our sampling rate is about, 44,000.
We can only express the values with a limited amount of precision.
Exactly.
So a limited amount of decimal places.
Yeah, so basically we're sampling it at various times very quickly, putting it into the computer, and then the human ear is registering those samples so quickly that it won't really be able to tell the difference between, what my voice is.
So when you're discretizing an equation, you're just taking it from that one of infinite precision and making it less precise.
Yeah.
And then, that if you're talking about digital circuits and digital filters, you have these things called coefficients. Mm-hmm. These coefficients, if any of you have used the DSP IIR, if you've watched that tutorial, mm-hmm. and you would see that there's something that says calculate coefficients. Mm-hmm. Those coefficients allow you to manipulate cutoff and resonance. And once you discretize your transfer function, you get your coefficients. So from there, you have to, test against the hardware to make sure it's okay. But that's pretty much the entire process.
Okay. So the coefficients. So once again, we're just talking about a mathematical. We're talking about basically taking a piece of hardware gear, and then we're trying to derive a mathematical function from it, which is transfer function, which is output and input. And then from this transfer function, we can get these coefficients, and the coefficients are really what determine the behavior of the analog gear. Would that be fair to say?
Did you miss a step? Before you get the coefficients, you have to do something, right?
So we have a transfer function. What do we need to do to get the coefficients?
Bilinear transform.
A bilinear transform.
That's what I said. That's how we discretize that function.
Okay.
Right. So we get the function from the circuits by analyzing the circuits. And we discretize that function, and we can use that function to get our coefficients.
Okay. Cool.
That's the process, and it seems very short, but the first step of analyzing the circuit requires that you have an understanding of analog electronics.
Okay.
And then the step of discretizing, that requires that you have something like, I guess there's a couple Python libraries, but like Mathematica or MATLAB to do it. And then implementing that into C++ or using Juice or whatever, it's fairly trivial.
Yeah.
But the other parts are the serious undertaking.
Okay.
Wow.
So this is maybe like a sort of a mid-level analog modeling project. I just wanted to sort of maybe say that there might be like a first level. And one of the assignments me and Josh worked on in first year was just like modeling a synthesizer. Like a lot of us chose like analog synthesizers. I remember doing the SH-101, and I did look at the circuits and stuff with like a very basic understanding. But actually, I went by these tutorials doing in Max MSP, just doing the 303, and sometimes when you start from these very sort of fundamentally quite simple synthesizers, just knowing how these individual parts fit together is a very good way of getting like a basic understanding of the electronics of the system. Right?
Yeah, so it's really about, because, for me, one thing that I always think about is, getting to that level where, you have, if you go into Max MSP or you go into Juice and you can build like kind of your bog standard, synthesizer or compressor, and then there's that next level, isn't there? There's the next level which is like, how can I take this and how can I add some certain kind of character, like a 303 character or SH-101 character, and, really like give it something that's kind of identifiable, or a little bit different from what else is out there on the market. So let's talk a little bit more about the circuit, this circuit analysis itself. So I know that we can't really, give like a class on electronics, electrical engineering here, but okay. So we were talking about this before, but just for the people here. So do I have to have, if I want to model a Moog filter, do I have to have the Moog filter right here in front of me to model it?
No, but you should have the circuit, and there are circuit diagrams out there that are not right.
They're not right. Okay. So you want so you find the circuit diagram, right? Okay. And as you were saying before, there are going to be parts that kind of matter and parts that don't matter, right?
There are certain parts of the circuit. So when you're doing analog modeling, you want to account for nonlinear behavior, which is like irregular behavior.
Yeah.
When one variable changes, another one changes in a way you don't exactly predict.
Yeah.
Yeah. So I mean, if you just have like something moving, for example, a linear movement would just be going the same speed.
Y equals X.
Or with the same, or if you're measuring acceleration, just the same acceleration. If it's non-linear, then it's going to be going whoop, 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 like an extreme example.
Or if you take the first derivative of that movement, velocity, that's not linear.
Yeah.
So when you have, like saturation curves, those are not linear behavior. But before we get sidetracked, like exactly what he said, and then that's what you are trying to account for. Now, there are certain pieces of equipment where you will need the actual thing you want to model. So some components themselves are nonlinear. So tubes or tube amplifiers, they're nonlinear.
Okay.
Vectorals, diodes, transistors, the same.
Yeah.
But you need either they're called like reference charts or like information booklets on that component. Sometimes you can't find that. Like if you're dealing with old Soviet gear, you can't do that.
Yeah.
A lot of stuff from the Cold War, you can't do that. But that's a lot of vintage audio stuff that people want to use. So you actually have to get your hands on the actual circuit if you can.
Wow.
Which will be really difficult.
So let's say, okay, I can't get my hands on the circuit itself. Am I just out of luck, or are there other approaches?
Well, I mean, as a very So if you can't get your hands on the diagram, okay, because there are circuits where you can get, like some people have, like a DIY audio communities have gotten vintage gear, reverse engineered them to get some semblance of a diagram, at least for the core part that you care about.
Amazing.
That might be a way you can go. And you can sort of like do some sort of trial and error of, swapping out this tube with this tube, emulation. But that's going to take some time.
Yeah.
It might not be very fruitful in the end. I don't know. Like that wouldn't be somewhere where I would want a beginner to start.
Yeah.
As a very last resort, if you can get samples of the output or putting in the input, that's called an impulse response. You can get those snapshots of the response for that circuit. That is a way you can go. There is a convolution plugin, because that's the mathematical process you're going to use to do that. There's a Juice convolution method in the DSP class, I think.
Yeah.
Who is it that makes that?
Waves. It's Waves.
No,
right?
I wasn't thinking about them.
Oh, really?
I
don't know.
They're Italian and Japanese. They have a red logo. Oh, yeah. I forgot this. I gotta look this up.
Okay.
Might have to do this.
While you're looking that up, I'm just going to explain in a nutshell about what impulse response is. So an impulse response, for people that don't know, is kind of like Will was saying, kind of a snapshot. So a lot of people think of impulse response and convolution in terms of a reverb. So like if you have a convolution reverb, those are reverbs that are based on real acoustic spaces, or most times it's based on like a linear acoustic space, so like a cathedral, and then you have a sound, and then you put the reverb on it, and it sounds like the sound is in that cathedral. So they do this through a process called taking an impulse response, which is where you're basically able to get a snapshot of what the reverb itself sounds like in the...
Or what it's affecting, how it's affecting the signal. So, so I guess you have a snapshot of it after and a snapshot of it before, and then, spot the difference type thing, you can tell what's happening to the signal.
Yeah, but remember what we were doing in, what was that class? PMC. I forget what it stands for.
Perception and multimedia.
Yeah, perception and multimedia computing. So, remember we had like a white, so it was like a white noise blast, wasn't it? That was the impulse response of that particular space. And then so you have the impulse response of the space itself, which is basically like a white noise blast that's recorded with a microphone. Is that right?
That's
And then
like a clap is in space.
Yeah, or clap. Yeah, clap. Something with a lot of frequency content. Because like a clap is kind of like a white noise blast, I guess. So you have then you have like this sound that's recorded, this like a white noise blast in this space, and then you have like a completely dry sound, like let's just say like a snare drum. And what you can do is you can do what's called convolving these sounds, where you basically take the space that we took the impulse response of, and you take this clap and you basically put them together in varying degrees, so like a wetness or a dryness. And then what you could do is it basically makes that snare drum sound like it's actually in that physical space. Okay, so that's a process that's called convolution. So impulse response is taking a snapshot of the way that something behaves at a particular period of time. Did you find the company? What's it called?
They don't sell it anymore, but it was a classic studio reverb, but they also, it's by IK Multimedia.
Oh, okay.
So that you could, put in the impulse responsive guitar amplifiers, and you could take on the characteristics of guitar amplifiers that were mic'd up in a certain way.
Wow, why'd they stop doing that?
I don't know.
That's crazy. I didn't realize IK Multimedia was Japanese. I didn't know that.
Yeah, they're Japanese and Italian as far as I might be wrong on that, but that's...
You do it really easily with probably Plus as well, but with Python, it's it's like a straight. You just take like a 1 second signal and you do a convolution function on. Yeah, it's like a pretty simple thing to do in code.
Well, it's a fairly difficult thing to implement in real time.
Yeah.
Convolution is a fairly complicated mathematical process to break down, but when with newer CPUs and newer architectures, and with the fact that Juice library is optimized and vectorized and everything, you can. So,
okay.
But so if you don't have the circuit, you can take impulse responses if you can get them.
Mm-hmm.
That actually implies that you can actually get physical hardware. But again, they're snapshots, so you have to take a lot of snapshots in order to be able to be accurate.
Yeah.
But and able to give your user something flexible to work with. Okay. But it's still necessary for certain types of things like vintage mics or vintage guitar amplifier cabinets. It's and it's something you still have to do if you're dealing with specific components that are impossible to find.
Yeah.
They're just things from the cool board.
Yeah. So you were saying that let's say that it's a filter that we're modeling, and we're doing various impulse responses or snapshots at various times. So correct me if I'm wrong. So it's taking the filter and is testing. So we're doing so we have let's just say it's a white noise blast, and we're basically taking the white noise blast, we're putting it through when the filter is turned all the way down on a low pass at 20 hertz, and then we do it at 30 hertz, 40 hertz, 50 hertz, all the way up, or maybe not every 10 hertz, but you know what I'm saying. So at various times in that filter, and then from there we're getting a difference between the sound that we're inputting, which is always the same, and then we have a sound that's coming out that's going to be different based on the different settings. And then
just to say the downside.
Yeah.
The downside is briefly just that you have more than just filter cutoff to deal with. You have your resonance value, which handles your Q value of the filter.
Yeah.
And you also have drive on some filters, including the Mo filter. So you have 4 things to deal with. And if you try to take a sample for every combination of each parameter, that's at however many, like you said, if you only took 4 cutoff values, still 4 combinations of 4 different
16.
values.
Yeah, so you're talking 16.
That's a lot right there.
Yeah.
And if you're talking about taking it every 10 hertz, which is reasonable, actually, you're talking about a large number of samples, and that's why it's not efficient, time-wise, productivity-wise, or even in the end, performance-wise.
So what do you do? So when you have this input and the output, let's just say that we're talking about one. Let's just say that we're talking about one input, one output. What do we do then? Is that how do we derive some sort of transfer function from that? Is it like a frequency analysis, or is it how do we actually determine what the transfer function is for that particular situation?
Jasper, is that you or me?
That's you.
Okay. Well, if you're taking an impulse response and you're trying to get a transfer function, you need more than one.
Okay.
You need to be able to establish the behavior over a range of values.
Okay.
And then you're approximating a function using some sort of numerical technique.
Okay.
That's how you would do that. But
I see.
That's why you would need a lot of impulse responses.
Yeah.
When I say using, like, you have a guitar amplifier and cabinet, you have that mic'd up a certain way. Mm-hmm. You take the impulse response of that, and then your guitar sounds like it's going through that cabinet. Mm-hmm. That makes sense. Like, mm-hmm. you could do that with adjusting very few values. Mm-hmm. You're basically just applying. The only things the only different samples you're taking are the distance from the cabinet and how off-axis it is from the cone of the cabinet. Mm-hmm. Mm-hmm. That makes sense in those particular cases. Yeah. But when you're talking about a circuit that you want a lot of control over, like a filter, like a compressor, then you need to actually, you could, come up with some sort of, numerical approximation using impulses, but it's more reasonable to assume that you have a circuit.
Yeah. Okay. So, and what we're talking about is something I had heard in a talk at ADC. I think it was somebody from Native Instruments talking about different approaches to analog modeling, and talking about basically what we call a white box approach, which is where you're taking and you're looking at the actual electrical behavior of the circuit, of each circuit that kind of matters or really is of importance, and then you're trying to do kind of trying to transfer that into software. And then we have another approach, which is this other approach of taking various impulse responses at different settings, which is what we call a black box approach. We don't know anything about the circuits that are inside, or we don't have any sort of electrical background to be able to really, analyze it properly. So what we do is we basically have a sound, we put it through the hardware gear, then we come out with with something different that's on the output. We do that at various times, and then from there we try to derive one mathematical equation from it. Is it one mathematical equation from it, or is it?
Transfer function is just one.
Yeah, so it's one equation. Wow, great. Okay, so let's. I don't know if this might be beyond the scope of this kind of tutorial, but like one of the first things that I'm thinking is, okay, cool. Now let me think about how I can kind of turn this into code if I'm doing a black box approach. Let's say we're talking about a black box approach where we have a series of impulse responses. We have an input, we have an output. Okay, I have these now, right? I have a bunch of waves that are these impulse responses. So how can I take this and like really start conceptualizing how to turn this into a piece of code that I could actually take and put in my Juice project? Is there an easy like answer that you could give me for that? Like something like, what's the most simple way that I could do that? Yeah, that's you. It's all you.
Well, if you have your impulse response, your function, and you take the FFT and you have the frequency response, and from there, you can create a sort of, if you have a set number of samples, you can always create an FIR filter, but that might be quite long.
Okay.
Right? You might get a lot of taps on that.
Okay.
Well, that's sweet. But you can always use some sort of discretization method, like I said earlier.
Okay.
I'm not quite sure. I probably have to think about that for a second. Like, Jasper, do you have?
Are we still on the filter?
So yeah, we're just saying in general. I guess we're saying just generally speaking.
I mean, I could do it in Python.
Yeah, but okay. So like, let's say you have I have this one sample, and then I have a bunch of So then I guess in Python it would be kind of just taking those and doing a convolve function, wouldn't it? Just
literally convolve it with the impulse response. Right?
Yeah, and then
it's the same thing in Juice. They have the same function.
Do they? A convolving function.
Yeah, so it's the same thing. But
Okay.
I mean, if you want to derive an equation, which is what you were asking, I don't know directly the best way to do that. Best way, I don't know. I know that you can use an FIR filter probably to do it, but it probably wouldn't be very efficient.
Would just convolving is convolving it in real time not very realistic?
No, it's saying it's doable.
Yeah.
I don't understand. Sorry.
Yeah. So we were saying in Python, I have this, I have a sound, I have an impulse response of a reverb, and I just convolve it, and boom, now I have the sound with the reverb, and I can control that in varying degrees, like kind of a wetness, a dryness type of. Is that so? Why would I want to go back and get a transfer function? Why would I try to derive a transfer function from if I say, okay, I got all these impulse responses, and so I can see what the behavior is, Why would I want to derive a transfer function rather than just saying, okay, I'm just going to take whatever I'm going to put through this filter?
It really depends on exactly what you're trying to emulate,
and also what
extent,
and also like how you want your user to use this. I mean, you could take the snapshot, the impulse response of the Moog filter at a given Q setting or a given resonance setting and a given drive and 4 different cutoff values, but that's all you have. That's not enough.
Can I not interpolate between them?
You can use some sort of numerical technique, or you can use some sort of machine learning technique to create the function that can do that. But there's already, that's still only assuming certain behavior.
Okay.
And think about doing like any sort of facial recognition stuff. And how many faces do you need before you come up with an algorithm that can sort of make some semblance of a human face? Same thing.
Yeah, no, it's exactly right. I mean, the thing is with interpolation, I think it's quite a nice area to do, especially if you just you just learn how to do basic logarithmic interpolation. Then it kind of is, if you're just getting into analog modeling and you just want something with a bit of character, it's quite a nice way, especially if you're doing that over the frequency spectrum for something. It's quite a nice way of just saying, okay, like I know that this is going to change logarithmically because it's on a frequency, like perceptually, it's on a frequency spectrum, and I just want to create like a few interpolation points, logarithmically along here, and then you're getting out values which are going to be slightly different to if you were just running it straight through, before you're doing your analog modeling of whatever. And it's quite a nice way of doing it, I think.
I have a really off the wall question that that I'm wondering. What if I wanted to model my software off of another piece of software? Like, let's say that. So like, okay, so let's say that I pull out my my Arturia mini Moog, right? And I just want to model the filter part, and I just want to model the filter of that mini Moog, right? Because they're going to be it's going to be a pretty robust. It's going to be pretty robust, isn't it? That filter emulation, right? Can I do that? Like, is that like a realistic or thing to do?
I mean, I think analog circuits for audio, there's a fairly standard way of looking at different audio circuits. There's actually a Wikipedia page that's pretty much dedicated to that. And it actually walks you through very, very simple first-order Sallen key filter. And how you make the transfer function for that.
Oh, wow, really?
And then you can do it yourself from there to discretize it and come up with it. And if you get it, if you understand how to do that one, like, I think you could probably do, the more complicated filters. And as I said, there's also one paper out there that's really good for how to do the Moog filter.
Wow.
I think and also the TB303. It's in the same paper.
Oh, cool.
So there are the resources out there that actually outline the entire step from A to Z, and the final part basically giving you the equations for calculating your coefficients. From there, after doing that, there is the fact that you should test this against hardware if you can, and even if you don't, and you don't decide to, fix for any sort of imperfections you'll get from, your approximation that you're making. There's all sorts of optimization stuff that you have to learn. Like it's, the mathematics get a little bit hairy for some of it. Some things.
Is it something that we could do a tutorial series on, like a really simple?
Yeah, I think so. It would probably take quite a few videos, though.
Yeah.
And the other thing I have to say is that when you're making, like, let's say you got a function, like a transfer function, and it's saying amplitude versus frequency, or whatever it's saying, like, or if it's the phase response, or whatever it is. When it came to interpolation earlier, I forgot to say that Juice actually has part of the library called the fast math functions. And essentially that allows you to make lookup tables. And you can interpolate between those lookup tables. And that's what's going to help you. Rather than, just making you should, if you're going to make some sort of impulse response and try to interpolate between a lot of them, you could do that. And that's partly necessary. But if you have like another function that you come up with, like the transfer function from analyzing the circuit itself, not taking impulse responses, because it's going to have a huge amount of precision. A large amount of that might be able to be taken out if you make a lookup table, and that's going to be more computationally effective.
Wow.
So there's all sorts of optimization stuff that you're going to have to do in here.
Yeah, for sure. Lookup tables are like a... Have you done a tutorial on lookup tables?
No.
Yeah, so that's like I think that's a really wicked technique for analog modeling and wave tabling and all these character sort of building things, basically.
Yes.
Wow. So when you say lookup table, do you mean just a vector with, or
it's like a dictionary, right? It's like a data dictionary.
Yeah, it's like holding a spreadsheet.
Oh, okay, cool. So like a CSV or a JSON then.
And then it's just holding all the values so that you can say, okay, I know that I have these values, but if I want something in between there, I'm going to choose to do a linear interpolation, or maybe a quadratic or cubic, however you choose it. But you can basically make it so that you don't have to calculate the value every time.
Yeah.
You're looking up a value from RAM. That takes one clock cycle. That's it. That's nothing. You don't have to calculate anything.
Yeah, exactly.
Wow. That's awesome.
So, I just sent a link
okay.
on the Wikipedia. Is that the list you're talking about? Wait, is that... Yeah, so there's this list, like Butterworth filter, Chevy Chev filter, elliptic filter, all these kind of things. Is that the list that you were talking about, Will?
I mean, these are important filters. I'm not sure if this was this.
We could find it, and I'll just put it in the description below.
Yeah.
After the video.
Yeah, like this is one page. This wasn't the one I was talking about, though. This is important. That
there's basically like different filters have different characteristics. You might have already taught, and a lot of these are quite usual in sort of analog circuit design and synthesizers and things like this. It might specify like Chevy Chev or something, and then a lot of the characteristics of that synthesizer will actually be down to the type of filters. So even if you don't have much understanding of analog circuits, you can sort of go and see, they labeled this with a particular filter type, and just knowing that can help you give some of that warning.
Here, I sent one link that has the one I was talking about, which has actual circuits on it. That's just talking about very simple cell and key topology. Because it uses op amps, you assume that it's linear for certain parts. But, you can understand that even though this is, not really exhibiting any nonlinear behavior, this is a circuit. This is how you go from continuous to discrete. Or this right here that I just sent is the paper that I was referring to that has stuff on the mode filter and the TV303 and how to go from continuous to discretized, and giving you the equations and even the results. And you'll be able to see how you can even emulate like self-oscillation and oscillate.
Wow.
Okay.
Incredible. Cool. Well, I'll put those below in the in the description, so our listeners aren't trying to copy it down really quick. It just like appears on the screen for like 2 seconds and then it disappears again.
Like that university who just erases the board.
Cool. So I think this is a good place for us to kind of. I think that really rounds things up, quite nicely. And this is something I'm gonna strong arm Will into doing a tutorial series on where we actually kind of go through and take this and try to make maybe take.
I kind of want to refer to the paper, the last one that I sent you.
Yeah.
I want to get in contact with them and see if I can just say I'm going to basically be showing people how to do this step by step.
Yeah,
because it is a very, very, very well written paper, but I have to ask them for permission to use it.
Yeah.
Like, this is showing.
Yeah, that'd be awesome. And then that'd be cool because I know it's something I'm very curious about learning, and we can just go through and just make it, make an example, and I think people would really like that. Cool. All right. Well, I think we'll just go ahead and wrap things up here. But Will, Jasper, thanks for all your time and everything. And like I said, I'm going to strong arm Will into doing this series with me. And I think it'll be really exciting. So a lot of exciting things to come.
Right.
So until next time, I'll see you guys later. Say bye, Will, Jasper.
See ya.